Hi there, welcome everyone to today's video. Today we'll start talking about rotational selection rules and eventually get into rotational spectra. Okay? In previous videos we've been talking about rotational energy levels for molecules, right? And today we'll start talking about the selection rules that lead to allowed transitions for rotational spectra. So as just a review, right, the rotational energy levels are kind of broken up based off of the types of moment of inertia and the symmetries of the moment of inertia that different molecules have. You have spherically symmetric rotors, right, that have all three moments of inertia equal. Symmetric rotors have 2 out of the 3 equal, and the third is non-zero. Linear rotors has 2 out of the 3 equal, and the third is equal to 0. And then asymmetrical rotors, right, have all 3 not equal to 0, right? And we don't really focus or talk much at all about asymmetrical rotors, right? We derive these energies in terms of J and K quantum numbers, right? And they're basically the same type of looking energies as your typical 3-dimensional rigid rotor energy, right? I mean, linear molecules, it is in fact the 3-dimensional rigid rotor energy, right? We just use J instead of L, right, for that energy, okay? But symmetric rotors and spherically symmetric rotors are very similar, okay? Spherically symmetric are actually, I believe, the same thing, right? And then symmetrical rotors have just an extra term that deals with K, right? So today we'll start talking about the selection rules for rotational spectroscopy, or microwave spectroscopy, as it's also referred to. Okay. So if you want a molecule to undergo some type of pure rotational transition, the molecule has to be polar, i.e., it has to have a dipole moment. Okay, right? You can think of that, right? That if you have some nonpolar molecule, that's what I'm representing with this purple molecule here, right? It has no dipole moment or things like that. It's nonpolar. Okay, think of the helium atom, right? Something like that. Okay, or even something CH4, right? If this thing is nonpolar, okay, then in order for this molecule to rotate, right, the electric field's got nothing it can do to it, right? Because light coming in, right, as we recall, is an oscillating, right, electromagnetic field, right? That's what light is, right? This is oscillating electromagnetic field, right? So if this electric field is going to induce a rotation in this molecule, right, how? How is that electric field going to somehow cause this nonpolar molecule to rotate when it has no type of way to interact with the molecule, okay? Because that electric field is not interacting with any dipole moment, right? Any dipole moment on the molecule, right? While if I have a dipole moment, so you imagine, right, a dipole moment is created when you have a positive and negative charge separated in space, right? This creates a dipole moment, right? And this has a certain type of electric field, right? Where this positive end and negative end want to be oriented differently to electric field, right? So as shown here, right, my electric field is pointing in the right direction, my negative end wants to be to the right, my positive end wants to be to the left, right? Well, now, right, if this is an electric field that's created because of light, right, a light, again, light is an oscillating electromagnetic field, okay? So this oscillating electric field will then introduce an oscillation into your molecule, right? Because, right, as your electric field goes up and down, right, your molecule at this point is going to be negative, positive, then at this point it's going to be positive, negative, and then negative, positive, then positive, negative, and so on and so forth, right? And so as this electric field, right, this is kind of your electric field from your light, right, as that electric field is oscillating up and down and up and down, right, it's causing the molecule to rotate with that electric field, because as the electric field is moving up and down, the positive or negative end of the molecule wants to move according to that electric field, right? And so this is going to cause your dipole to start rotating around and around and around with this electric field. It'll rotate at whatever frequency that light is at. Okay? And so for your molecule to absorb that light, right, and have that absorption of light induce a rotation, there's two criteria that need to be met, right? Two kind of gross selection rule type criteria is one, your molecule has to have a dipole moment, right? This is what's going to consider the gross selection rule. It's if your molecule has no dipole moment, never going to absorb light to cause a rotation in that molecule. Okay. And the other selection rule has to do with what energy levels are allowed to transition, and we'll talk about that in just a minute. Okay. But related with this light, right, having to induce a rotation of the molecule due to the molecule having a dipole moment, right, is we've talked about before in quantum mechanics how energy levels are discrete, right, which means that what frequency I can rotate at, right, how fast I can rotate is at discrete rotational speeds. There are certain speeds I can rotate at, right? So if the frequency of my light is oscillating at a different frequency in which my molecule can rotate around, okay, then the molecule is not going to absorb the energy from that light, okay? And so that light has to have the correct frequency to be absorbed by the molecule, okay, based off of the allowed rotational energies that the molecule can have, right? And that molecule has to have a dipole moment, okay? And again, you can think of this frequency selection, okay, we'll see it more mathematically in terms of energy gaps and things like that, right? But you can also think of this frequency selection, again, like trying to find resonance with a glass, right, and causing the glass to shatter, right? That you can vibrate a glass and it will vibrate at whatever random frequency you try to vibrate it with, right? But that vibration kind of dissipates, it doesn't do anything, it doesn't cause any drastic change in that glass, right? But if you vibrate at its natural vibrational frequency, okay, then it keeps on absorbing that vibration and you're just adding to it, right? It's like pushing someone on a swing, right? You push the person at the frequency that they're swinging and they will go higher and higher and higher. But if someone comes back to you while you're swinging and you try to push them forward, it's just going to cause them to say stop, right? And so that buildup of energy, right, you're building up kinetic energy when you're swinging. So that buildup of energy is only occurring if you're pushing them at the frequency in which they're swinging, okay? And so that is only when you can absorb that light, is when that light is pushing your molecule at the frequency in which it can swing, if you will, right? In which it can rotate, it needs to have the same frequency as that light, okay? Right, and so this is kind of just classically explaining some of these quantum mechanical effects we see, right? So you can't use classical mechanics just to help understand a number of things that occur in quantum mechanics, okay? So now let's talk about the specific selection rules, okay? Right, so we assume the molecule is polar, okay? Right, but now the question is what other selection rules exist, okay? So the selection rules, right, the molecule has to be polar, and this transition dipole moment, right, needs to not equal 0, okay? The transition dipole moment is the integral of your wave function with respect to the, this dipole operator, right? Your wave function can be broken up into a rotational, vibrational, electronic part, okay? Right, we're assuming that this transition dipole is only interacting with the rotational part for the sake of rotational spectra. So the electronic and vibrational wave functions kind of integrate out as one because they're normalized. So I'm just curious of this integral not equaling 0. Okay. Now, given the functional forms of the rotational wave functions, the spherically harmonics, okay, and then what the transition dipole moment operator looks like, right? You can work out mathematically, okay, that the selection rules reduce down to this here, okay? That your J value, this is sort of like, again, if we want to think of these selection rules in terms of orbital angular momentum, right? You would think of this like delta L is equal to plus or minus 1, right? And then M sub L, right, equal to 0 or plus or minus 1, right? So what this is saying, right, is that your rotational energy state, your J value, can increase by 1 or decrease by 1 through the interaction with light, and then the M sub J value can stay the same, or again, it can at most increase or decrease by 1, okay? So these are referred to as like the specific, right, selection rules. Okay, right. So those are the specific selection rules. Right, the gross selection rule is just the molecule has to have a dipole moment. All right. So for the right, for these selection rules, right, you can kind of see where they come from. Again, like we did for atomic spectra, right, where light has an angular momentum of 1h bar, right. So to conserve angular momentum, right, your total angular momentum has to change at most by right. This J value has to change by plus or minus 1. Okay. And so that's why, right, so then for absorption, your J value has to increase by 1, right, because you're absorbing, so you have to go to a higher energy state. For emission, your J value has to decrease by 1, because again, you're giving off energy, so you got to go to a lower energy state, right? Right, and so, right, so again, you can kind of think of this specific selection rule about the changes in J's dealing with conservation of angular momentum, right? So for symmetric rotors, there's an additional criterion that the K value cannot change. Okay, so right here we have the energy for symmetric rotors, right? This is for symmetric rotors. Okay, and so for those symmetric rotors, right, the K value cannot change, so delta K is equal to 0. Okay. So the convenient thing of that is that the energy change between your initial and final state will never depend on K because K never changes, right? K cannot change, so that delta E, right, whatever your change in energy is between your initial and final state, right, this will not depend on K, right? And so, okay, and so that actually makes it a little bit convenient that the spectra for symmetric, linear, and spherically symmetric rotors end up looking very much identical to each other because of this selection rule here, right, that delta K cannot change to an absorption or emission event. Okay. So to wrap up this lecture, we're just going to talk a little bit about the Stark effect, right? So before I talked about how, right, your molecule, right, that there's this m sub j value related with the right, rotation with respect to some arbitrary axis in your lab, right, some lab axis, right? This is to do with rotation around lab axis, right? And so this m sub j value, right, can take a bunch of values here. There's 3 different ones depicted, right? M sub j equaling j, okay, is this first one, right? This is equal to j. M sub j equals 0 is the third one, right? And so there's these different ways your molecule could be oriented effectively while it's rotating around the laboratory axis, right? Again, I can think of this pen rotating, you know, around my laboratory axis like such, or this pen is going to have the same angular momentum no matter how I orient the pen around the laboratory axis. Okay. Well, in quantum mechanics, that orientation around the laboratory axis is quantized, right? And the Stark effect has to deal with the fact that the degeneracy that we referred to before, right? So this rotation around the laboratory axis just introduced a 2, you know, times j. Oh, sorry, not 2 times 2j. Let's fix that, right? This is, right, it introduced a 2j plus 1 extra degeneracy because of this rotation around the laboratory axis, right? So the Stark effect is essentially when this is broken, and this degeneracy is broken when you apply an external electric field, right? Because if I have a polar molecule, right, say like carbon monoxide, right, that has a polar linear molecule, right, the carbon and the oxygen end of that molecule is going to want to be pointed differently in a electric field, okay? And so that is going to then change the energy of this molecule when it is oriented differently with respect to the laboratory axis. Right, so the effect this has, right, kind of shown in this energy diagram in the bottom right here, right, is that when you have the field off, you have a bunch of degenerate levels, right, and then when the field is on, these energy levels get split, right, into a bunch of different energy levels because, again, the molecule, right, we're assuming the molecule is polar because otherwise it doesn't have rotational spectrum, right? And so then that molecule has then a bunch of different states that are now available to it, okay? And the energy change that's occurring due to this external electric field has to do with the dipole of the molecule, right? So this mu is the dipole of the molecule, right? M sub j is that quantum number, and then E naught is the strength of that electric field that you're applying in your laboratory axis, okay? Right? And so the Stark effect can split a lot of this degeneracy and give you information about where your molecule is oriented and other things of that nature as well, okay? And so that's going to be it for today's, not necessarily today's video, but this video, right? Talking and introducing the selection rules for rotational spectra.